It's joint work with a bunch of people, Thomas Hainer, Sam Jacques, I hope I pronounced that name correctly, Michael Nerik, Matthias Söken, and Fernando Verdia. Fernando is here too, over there. We were super happy to have two brilliant interns last year, Fernando and Sam, and the lion's share of that work is due to them. So the idea of that work is basically the other end of the spectrum compared to the asymptotic analyses we heard about in the morning. So what we want to do is we want to cost out, basically at the bit level, the cost it takes to break some crypto schemes. So the schemes we're looking at here are AES on the one hand and low MC. So those are the two schemes we implemented. And on the exponential speedup side was Shor's algorithm, in particular for elliptic curve D-logs. So I'm going to show you how to implement those algorithms in Q#. And first I want to introduce real quick what that is. So Q# is Microsoft's programming language. There are many, many programming languages, and many of them are really great. Microsoft has their own flavor. It's called Q#. It's part of a bigger offering called the Development Kit, and part of that offering is Q# with a compiler. There are simulators and resource estimators, and I'm going to say a little bit more about what they are in a moment. And what's important is there are a huge chunk of libraries. Libraries is what you need to get started to actually write down algorithms. There are already several libraries out there. Samples are examples that teach concepts in the language. There are also many here. And what we really love is katas. Katas are really simple exercises ranging from just implement a Hadamard gate to implement Deutsch-Josa and beyond. But there are things that are self-paced. You can start learning the language that way. And you always get immediate feedback. There are unit tests that you write. You have to pass all the unit tests, and that's how you learn the language. It's all free. It's under the MIT license, so it's an open source license. You can contribute back to Q# if you want to. And also the work I'm going to show here is also open source, so it's available at that address. And roughly the idea is the following. So we want to have a language that's very high level. Ideally, we don't even have to reason about circuits. So you can reason about circuits, but you don't have to. That's the aspiration. Because circuits are not really a scalable concept, right? When you think about it, having thousands of qubits, having billions of gates, you don't really want to think about the circuit so much. You definitely don't want to visualize the circuit anymore at that level, right? You want to get metrics about the circuit, but you don't want to look at the circuit. It's all black in a sense, right? Once you have that many qubits. So the idea is to express a program high level and at scale. And the language allows you to do that. We distinguish two different types of operations. So operations themselves are the true quantum operations that you write. Think about Hadamards, Cliffords, T-gates, and so on. Whereas functions are classical helper functions you might need on the way, right? Think of it like that. You do a measurement. Based on the result, you do another decision, what you do next in your algorithm. So you get that adaptive flavor of your algorithm. To support that, we have functions. There are libraries to implement both, but the user then typically, he or she writes a program that uses those and have their own operations and functions. It might also have a driver, a classical program, where you just gather and then you post-process what you learned, right? Shor's algorithm is a good example. You do some continued fraction expansion at the very end. It's entirely classical. It can be offloaded into a classical programming language. Once that's all written, then you can target various backends. So, of course, we'd like to target quantum hardware. Scalable hardware doesn't exist yet, but the program that you write today, in the future, you don't have to modify it. You can use it and run it on the hardware, ideally, once it's there. In the meantime, you can run it against simulators, and you can run it against resource estimators. So resource estimators, what's that? Well, basically, it's a profiler, right? It runs through a program. It counts how many qubits are there, how many T-gates are there, how many C-naughts, what is there, right? What is the basic profiling information? So what you see here is a chemistry application, and we implemented here two different methods to do the same, basically Hamiltonian simulation. One is trotterization, and another is qubitization, which is a method we heard in the morning about. It's a block encoding technique. Both are implemented in Q#, and you can use it to do, well, up to some size, of course, right? You can do resource estimation of those Hamiltonians. And what's also cool is if your circuit belongs to a special family, say Clifford circuit, we have a classical algorithm to simulate them, right? And Toffoli circuits as well. If you have just a classical input to your Toffoli, then you can still simulate it. Of course, not a general input, but if it's classical, a bit vector, you can simulate it. And there's support for that in the language. So that's good to write unit tests, right? So you express your entire Shor arithmetic as a Toffoli network, and then you test it out and you find bugs early on. Okay, let me talk a little bit about how we do AES. So this is what it looks like in Q#. So don't worry if you can't read it. So the bottom line is just, it's really literally the loop you would expect over square root of capital N many iterations, and then there's an iteration of 2 reflections, right? Alternation of 2 reflections. When you drill it down, basically it's, as you all know, it has the sequential flavor, right? Many applications of the same operator. And when you drill that further down, as you pop it open, there is this, what we call in quantum computing, oracle, right? Where all the complexity really sits. The rest is basically just an AND gate and a bunch of Hadamards. And when you drill that further open, for a special case of AES, then you see several boxes that implement the cipher, the forward evaluation of the cipher reversibly. Right? So that was state of the art. Like a couple of years ago, we thought we need 3 boxes for 128 bits, 4 for 192, and 5 for 256. Those are the 3 flavors of AES. Turned out that was actually very wasteful analysis. So part of the last summer, when Fernando looked at the problem, we realized that you need only 2 boxes for 128 bits, 2 for 192, and 3 for 256. There was another group that came to the same conclusion around the same time. I'm going to mention them later. But kind of that already chops down the number of qubits significantly. It also chops down the number of gates. But there were more improvements. And so let's look at the algorithm a little bit closer. So AES forward consists of just like key expansion and then many rounds where you have an S-box internally. And the S-box is essentially finite field inversion. So we implemented that in Q#, and the most of the savings came by a smart way to do that S-box. So there's a great paper. It's a classical result by Boyer and Peralta. And they came up with a very low complexity implementation of the S-box. And complexity is measured in terms of how many AND functions you need. That's called the multiplicative complexity of the function. And that chops down already significantly, as you can see, the C-naughts and the T-gates. T-gates are the dominating cost in fault-tolerant implementations. It was a slight increase of qubits, but the T-depth savings are dramatic. And there were further savings that we found by improving the key expansion. Key expansion before was done in a wasteful way. The qubits were not reused, and it's possible to reuse qubits often. And that you can see that drop here. This code is available. We have a paper, and you can get that code for free. Oh, okay, I should mention this as well. So this is a special Easter egg that NIST left us in the call, namely introduction of max depth, right? They said, okay, no quantum algorithm can use more than that depth, right? And they gave 3 choices, and there were justifications for those choices. But what it really means is that we had to reason about, hey, what happens if the max depth is 2 to the 40, if it's whatever, right? Then we're forced to parallelize, right? Because you cannot do a deeper computation. And Grover, unfortunately, does not parallelize well, right? It doesn't like classically, you can chop, if you have 2 processors, you can distribute ideally the load, and you can double the speed, right? Quantumly, unfortunately, that's not the case. So, but still, we had to analyze it, and the result of the analysis can be found in the paper. It heavily depends on what your max depth is, what you can achieve. We improve over the best known state-of-the-art by several orders of magnitude. Basically, three orders of magnitude are our improvements. Of course, still these algorithms are not algorithms you want to run. This is all just about the security parameters of those schemes, right? Nobody wants to run a quantum algorithm with that many gates. But we have these rough estimates. And as I said, the papers, the code can be found online. Also, I can quickly show you. So there's a GitHub repo where you can clone it. And then if you want to run, you can just, this runs across many different platforms. If you can type, it should work. It runs on, oops, this doesn't pick it up. This is interesting. I'm on a virtual desktop here. Oh, this apparently does not do it. That sucks. Okay. It is, yes. Maybe I have to exit the PowerPoint. Switch to virtual desktops. Yes. No. Okay.
Merge the 2 screens. PowerPoint shows you.
It slows me down 3 orders of magnitude. So.
No, you can lower it. Like where you have the external screen and you
yeah.
duplicate. Same split.
Oh, shoot. Okay, that's a good point.
Shows your notes on top of it.
Duplicate the screen.
Microsoft. It's like such a big system.
One extend.
It's not an implementation project, it's nothing.
Sorry, folks.
There we go.
There we go. Okay.
Yep.
Okay, so sorry about that. So you can clone the code on GitHub, and I just wanted to show that real quick. This is what you can do with it. So AS, for instance, those are the files that support it. You can look at the code. For instance, in Visual Studio Code, see the code here. If you want to run it, it runs across multiple platforms. You can run it on basically whatever supports .NET Core, and that Macs do support it, Windows, Linux supports it. And then this gives you the Oracle itself. It gives you the resource estimates, the T-gates, the C-naughts, and so on. And you can modify this stuff. If you have your own hash function you want to implement, basically all the infrastructure is there. You can run it.
So what does it do now?
It goes through all the components that are needed for AES. There are all these kind of key expansion, sum key, and kind of it goes through all of them, picks up the cost, and at the end you get also the aggregated cost. Then you have the cost for the Oracle itself. What we did then, the rest of the analysis we did by hand, like the reasoning about parallelization of the algorithm, we did that part by hand. Does that answer the question? Okay, let me shift gears and talk a bit about D-log. Because at a high level, it's a similar approach. We write a library for the point addition. But of course, the arithmetic there is very different. So whereas in AES, you have a lot of bit-level operations like bit-level addition or XOR shifting of bits, ECC D-log is dominated by modular arithmetic. That means, like, kind of have a look at this. This is typical, a typical formula that you can find on Dan and Tanya's database of like point addition formulas that are out there for elliptic curves. There are many, many ways you can represent a curve, and there are many ways you can implement the addition. We picked one. We picked a affine Weierstrass form for the elliptic curve. And then what you face is a lot of finite field operations, multiplication, addition, inversion. And inversion is by far the most costly operation, as you might imagine. Because how do you do actually inversion? Well, you have to do a Euclidean algorithm. And the twist here is that you have to do it reversibly. So you have to, in superposition, you have to invert elements. And the twist is that the Euclidean algorithm does not have a uniform runtime, right? The different inputs might require a different number of steps. So you have to uniform it, kind of make it uniform, that you do the exact same operations no matter what the input is. So that's the complication here. We used a particular representation of the numbers called Montgomery representation. And then it looks essentially like the binary Euclidean algorithm, what you need to implement. So we had done that earlier in the paper in 2017, but it was wasteful. So in the internships, what we found was that one of the registers could be flat out eliminated. It was completely unnecessary to introduce that. And instead of 4 inversions here, we could actually get away with 2. And also there was an unnecessary squaring step. So all these things together led to reductions in qubit count and gate counts. And then if you look at the table, that line here was the previous known best results, 2 to the 39. And we brought that down by almost 2 orders of magnitude. So instead of 100 billion T-gates to do Shor 2000 bit, it now, in quotes, only takes roughly 1 billion T-gates. And the number of qubits also came down, mainly by eliminating that one register. If you compare it to RSA, there's a whole technology about comparison. I don't want to get into there. But one school of thought compares 256-bit of ECC to RSA 3000. And when you look at the qubit numbers there, they're higher, and also the T-gates are significantly higher. And the takeaway from there is it's easier to attack ECC D-log for comparable security parameters than it is for RSA. The techniques were unrolling of while loops. That was the main improvement. But also windowing was a technique we used. And we basically learned and adapted techniques there. We learned from a paper by Craig Gidney and Martin Elkara. They introduced these techniques, and they're very powerful. They lead to a lot of savings in the gates. And that's it. Thank you very much for your attention. Thank you.
Any questions? Yes. Sorry, I just wanted to check I understood correctly. The improvement in Shor just came from doing more efficient elliptic curve arithmetic?
Good question. So the question was, does the improvement in Shor's algorithm come only from doing better elliptic curve arithmetic? So there were 3 sources basically of improvement. One was to realize that we did not one of the intermediate results. We could basically do an in-place update of the variables. That was one. The other one was in the unrolling of the loop. There were several improvements we could do better, and there were local improvements like the squarer we could eliminate. And the third one was at the top level. When you look at Shor's algorithm, it has a bunch of bits, and then it does these conditional additions of multiples of a point. It's all classically known points. We did windowing at that level. So basically, windowing means you cache, you pre-compute some stuff, and you make small tables. And there's a sweet spot for the size of those tables. So we did that, and we then got the improvements. And mind you, those are all implemented. The entire arithmetic is all implemented and tested at scale. So those are the actual circuits that you would one day run on the computer. And we run them through to test vectors, and they're all correct. So the only quantumness missing is the Hadamard and a phase gate and another Hadamard. And the rest is all this classical arithmetic that happens in between. And that's all implemented here. And Q-sharp, basically, you push a button, it counts all the gates, and it checks it.
So
That's it.
You want different optimizations for the quantum setting and the classical setting? Is that why it is?
Oh, that's a great. So the question is there different optimizations quantumly versus classically? The answer, I think the honest answer is we don't really know yet. Classically, people optimize, for instance, Dan, Tanya, correct me if I'm wrong, optimize for squarer, because squarers are cheaper than divisions, right, classically. So we don't know if the same intuitions hold true here. It would be actually great to try out many different group representations, many different group laws, and do an automatic estimates. One complication, there's some technical complications there due to which we have not been able to go beyond Weierstrass forms so far. It's not so easy to work with projective coordinates on a quantum computer if you really want to do it at the bit level. And that's the main issue. I don't know if that answers. Okay, cool. Alex had a question. Harry had a question. Okay. Here.
Is it logical qubits, or do you already include error correction?
Good question. Is it logical qubits or physical qubits? One answer, 2 questions.
Well, it depends on what you're going to say now.
Okay. So choose my words. Wow. Yeah, all logical. Yeah. We could do a footprint type of analysis where we just multiply the number out, not taking into account any more sophisticated mapping of the circuit. But this is all logical. Does that?
Yeah, because I'm sort of a little bit, well, not puzzled, but this non-parallelization of Grover is sort of difficult.
Yeah.
You still seem to have some advantage in your analysis with, I guess, a reasonable width, I think you called it.
Yeah.
But now if you take error correction into account.
Yeah, that's a good point.
Maybe you don't have a...
Yeah. Yeah, the question is whether if we take into account fault tolerance and error correction, if we still have an advantage. And I think the honest answer is we don't know, because the overhead could be quite significant for making it fault tolerant. Yes. And Vlad, yeah?
So how did you have Toffoli networks, I guess, right? That's how you test these circuits, or because otherwise I don't see how you can.
Yes. Yes, the question is if we have Toffoli networks underlying the circuits. And yeah, the answer is yes, we do. There is one little twist to it. So we have to write the unit tests and to test the circuits, we use the Toffoli networks, because then we can feed in a classical test vector, send it through the Toffoli network, and check if we get the right test. To the resource estimates then, we can do a little bit better. Like a Toffoli simply, naively, maps to 7 T-gates, but there are ways to do a Toffoli with 4 T-gates and measurement, right? If you have 4, like Gidney has a paper, I think Salinger earlier had a paper. So you can actually do it by 4. So you get like an improvement of 4 divided by 7. And we didn't want to miss out on that improvement. So how did we do it? Well, the same Q-sharp program once can be run against the Toffoli tester, but then you can run the same program and run it against a way to map the Toffoli to different T-gates. You see, in the resource estimator and the tracer, we then had a different way to break it down. So we actually, the numbers we report, use the 4 T-gates per Toffoli gate. Does that answer your question?
Any other questions? Okay.